Thank you. Thanks, Pasha, and welcome everyone to this session. So I'm Jitin from Microsoft. So I lead the performance optimization team at Azure HPC. So this session, like I have organized in a simple manner, like we can go over a quick overview of the of Azure HPC. We can go a high-level overview of the two different representative SKUs, HPV3 and NDV4. Two of the latest VM type. And since all of us are passionate about network, I would like to list out the different network features that are offered and on the clusters, and specifically on the Azure HPC VM images, like how we can quickly deploy a VM and then make use of middleware such as UCX and ready for communication. Some performance highlights. I'd like to show some benchmark results on HPV3, NDV4, and some scaling results, and conclude with that. Azure, as most of you know, like it's a really global infrastructure. We have like data centers typically like almost all around the globe. And different edge clusters also. So truly a global infrastructure. The main advantage is that you can have data reside close to your compute and close to your clusters. And you have service availability and like with competitive pricing. I don't want to go too much into the detail, but the main idea is that like you have different types of VMs for different class of applications. But in this session, I would like to focus on the HPC/AI VM types. So broadly, we can classify it into H and N, where H is the standard HPC applications where you have high compute and high memory plus high-speed network, which is InfiniBand. Azure is the only public cloud that offers IB on cloud. So that's the H series. An example HPC SKUs are HB, HC, HPV2, and HPV3. We'll go into HPV3 in some more detail in the following slides. And on the N series, it's basically the VMs with accelerators. So it can be, broadly, it can be classified into two again. The visualization SKUs, which is the NV series, where your typical workload is just maybe a single node, etc. And the deep learning or AI SKUs or even HPC SKUs, right? So that's the NC or ND series where we have accelerator plus high-speed network, right? So that's the NC and ND. And quickly, to identify, say, if a VM type supports IB or RDMA, is that so if the VM name has a little R, so that means it has RDMA support. And in all the IB-enabled VMs, we only have one VM per host. So you are not sharing, your VM is solely allocated to you. You're not sharing the host between some other customer, right? So that's a key. And also IB is exposed to the VMs using SRIOV, so complete host bypass, and you'll get the full feature support, right? And also you have PKey or partition key based isolation, where in the same cluster, there might be multiple customers running, but any allocation from a single customer using a single availability set or a VMSS, like those are terms where we use to group a set of VMs. So those VMs will always all have the same PKey, and they'll all be able to communicate only between that particular group and not to outside. So that's how we ensure isolation in terms of network. Let me go a little bit deep on the two representative SKUs, HPV3, which is an H series, and NDV4, which is a deep learning SKU, right? Two of the latest ones. HPV3, so this is how we design it. So, I mean, the main design goal is to like minimize any jitter from the host and or any jitter from any agents which are running on the host or the guest, right? So here, I mean, this queue is actually based on the Milan X. Milan X, as you many of you know, like it was announced earlier this month. And on the same day, we have the preview clusters ready for customer access. So this is how we design it. So we have, again, this is configured in NPS equal to 2 configuration, that is NUMAs per socket, that's 2. Even in the same NUMA node, like we take out a certain number of cores for the hypervisor. 2 from here, this NUMA node, 2 from here, and 2 from the rest of the 2, right? So total 8 cores set back for hypervisor. So when the host boots up, it will see only these 8 cores. So any the Windows OS or any agents which are running on the host, it will always be using only these 8 cores. And the rest of the cores are all available to the VM. So that way, and the VM cores cannot land on the dedicated host cores. So we configure this using something called minroot, which is a Hyper-V feature. So that way we can ensure that there is no jitter whatsoever from host or from the VM activity not impacting host also, right? So both ways we ensure isolation. This queue has a CX6 NIC, and we offer these in different configuration. So we can offer all 120 cores, or if you want to pick, say, certain cores from each CCD, right? So 6 per CCD, that is 96, etc. And say for 1 per CCD, that's 16 core VM. So that's mainly to help with, say, certain applications that have the, say, licensing constraints, etc. So which is based on core count. So this way we can ensure you get the best performance, and at the same time, I mean, you're not overpaying for the license cost, etc. And one of the cool things here is that it has L3 cache of about 1.5 GB. I mean, it is almost 3x as compared to the previous version of HPV3, which is Milan. And you will see the benefit of the L3 cache coming into picture in the scaling graph. So I'll have some data towards the end of this session to show that. So that's Milan X HPV3. The other one is NDV4. So this is one of the most latest deep learning SKUs that we have. Again, I mean, similar design ideology. So here also we take out a certain number of cores per each NUMA. So 8 cores per NUMA, so 32 cores are taken out in this case, and the rest 96 are given to the VM. So interestingly, like, so this queue has 8 A100 GPUs and 8 CX6 200 gigabits per second IB NICs. So it's a massively powerful machine, yeah, I'll show some results towards the end. And this has made up into the top 500 in this list, so top 10 ranking. So we'll show that later. So basically, that's these two representative SKUs. I just wanted to give a highlight of how we define the SKUs and how I mean, we ensure that there is no jitter from host or no jitter from other VMs, etc. Right? Some of the network features that are available on Azure. For example, I mean, we have different types of SKUs, right? So CX5 based older generation SKUs, and the newer ones have CX6, 100 gigabits per second, and then 200 gigabits per second, right? And all the different features that we are very much familiar on the bare metal side, like DCT for the scalable transport, hardware offload, I mean, both for collective offload and also hardware tag matching. UD-based MCAST, Sharp. I mean, I'll have some Sharp results later. Dynamic routing, advanced congestion control or adaptive routing, and also better reliability with Shield, right? So, I mean, all these features are exposed. to the VM. What is not exposed is, we don't expose the QP0 for because of security restrictions. So, the VMs may not have available, provision to run, say, IB Diagnet or IB NetDiscover from the VM. But you can always get that using special tools, etc. Right? So that's not a limitation, but I'm just giving the full picture. Yeah, so since we covered the different network features, I just wanted to quickly share some of the results also, right? So GPU direct RDMA, I don't have to explain this feature because all of you know this. So basically it provides a direct DMA path between the different GPUs on internet, right, or network, right? So on this graph, on this slide, I have shown like two different screenshots. One for the RDMA host memory, like all eight IBs doing IB bandwidth, and each of them getting the peak close to the 200 gigabits per second peak bandwidth. And at the same time, so this is for GPU direct RDMA. In this case, at this time, it's all simultaneously doing the GPU direct RDMA transfer. And you can see all of them again reaching close to the peak performance, right? Peak bandwidth. So collectively, this queue can like push out around 1.6 terabits per second at the same time, right? So, and since we export, export the IB over SRIOB, it supports all, complete support for verbs, or so that any GDR capable MPI or libraries can make use of it, right? The next one is Sharp. Sharp is currently not enabled on all the clusters, mainly because Sharp resources are constrained today for the HDR switches, right? But that's something that NVIDIA is addressing in the next generation. But so currently we have enabled Sharp only on dedicated NDV4 clusters. NVIDIA team has done like several optimizations to enable Sharp on cloud environment. So one of the cool things is UCX-based Sharp AM or Sharp D communication, because now you can get the PKey-based isolation for this communication rather than going over TCP/IP. Optimized Sharp tree initialization, which really enables you to like scale out to really large scale. And also connection keep alive so that you can reduce the traffic to the UFM or the Sharp AM in this case, right? And also GRH support, like so that again, if you want to like really scale out, to support that. So in the graph, I have shown two lines here. One is with Sharp and without Sharp. So you can see we are hitting around 227 or 220 gigabytes per second. Without Sharp, it's about 189 gigabytes per second. So again, this is very much close to the peak performance here. So 200 gigabits per second NIC, and all of them, theoretical peak is around 200 gigabits per second. So we are reaching around 190. And then with Sharp, now we can see it is now limited by the the NVLink performance. So about 227 gigabytes per second, again close to the theoretical peak. Congestion control. We'll have some detailed results. Especially with the application results coming in on Wednesday's session. In the cloud native supercomputing performance isolation. So here I have captured GPCnet results for say 512 VMs all running at the same time, right? A group of them doing creating artificial noise, and other ones doing the benchmark. Two configuration, one is CC disabled and CC enabled. And for the three different benchmarks, the latency, bandwidth, and all reduced, right? So you can see, and the graph is actually plotting the congestion factor. Ideally, it should be 1. Basically, it is so ideally it should be around the 1 mark, right? So we can see without CC, it's all around the mark, right? And then with CC, it's very much to the ideal performance. So same story here with the bandwidth. And also the all reduced. So we can see, and this is really important in case of public cloud, because we have multiple customers running their workloads at the same time. I mean, even maybe on a supercomputer, you can like traditional supercomputer, you can just do a like check your queue and see, I mean, what other customers are running, etc. But I mean, cloud, you cannot see what other customers are running, etc. Right? So see, congestion control really enables you get the best performance on consistently in this case, right? So we are still in the experimentation phase. We haven't enabled it all across, but our plan is to enable congestion control on the fleet wide, very soon. And the other one is adaptive routing. So this is again a quick illustration of how adaptive routing can help here. This is an this is very interesting actually. So this we saw a big performance dip even on a 4-node job with say static routing. And then we mapped out the actual the routing paths that it takes, and then we found out this one particular link was used for the 2 different communication paths, right? So let me go into a little bit deep here. So this is a logical ring, like 4 ranks A, B, C, D, so 2 ranks on same rack. So these are 2 different nodes, and 1 node here and 1 node here, right? And we have IB0 switches, which is the leaf switch, and then IB1 switch, which is the higher level switch. So, I mean, if we do the static routing, right? Say, for example, destination-based routing. So A, if it wants to talk to B, it will go to IB13 because it's in index 3 in this rack. So it will go here, and then 1A and 1B. Similarly, B, when it wants to talk to C, it will go to IB6 because it's in 6th position, and then here and then here. So to A to B, similarly 3A and 3B and 4A and 4B. So you can see 1A and 1A and 3A uses the same link and the same direction. So and we even when we measured the point-to-point performance for each of these, we saw this particular one was cut into 2. And with adaptive routing enabled, right, that effect is gone. So again, the nickel bandwidth results itself, but so here we can see adaptive routing disabled. We can see the peak bandwidth was cut into 2, like here, and then with adaptive routing, you can see it was reaching close to the peak again, right? So so it is enabled by default on the NDV4 and not on the HPV2 or HPV3 SKUs, because certain MPIs doesn't really work really well with adaptive routing. But you can always choose a different SL where adaptive routing is enabled and use that. So we have more details on adaptive routing and how it is configured for the different SKUs in this particular link. And finally, a quick note about the HPC VM images. So, we have the different networking features, technologies, etc. But how you can make use of it in the cloud, right? So one can easily deploy a VM based on the HPC VM images. So we have 2 flavors. The CentOS-based HPC VM image and the Ubuntu-based HPC and AI VM image. So both these images, we have all the different or mostly or widely used software packages. And it also comes with the recommended optimization configurations, everything. So the main idea is that like one can deploy a VM easily and then get out of the box performance. It has also the different MPI libraries, HPCX, Intel MPI, MapReduce to OpenMPI, and also UCX. So UCX, let me make a quick note here. So UCX is I would say, the most widely used or widely recommended transport layer for Azure, mainly because it gets you the best out of the box performance, and it's very stable also. Like for HPCX, again, it uses UCX, Intel MPI, again UCX, and OpenMPI also UCX. So we really recommend UCX for our clusters for this performance, etc. And some of the results I show now here, and also the different benchmarking stuff that we do are mostly using HPCX / UCX. So quickly, looks like not much time left, but so HPV3 MPI performance characteristics. So again, like I mentioned the skew and how the NICs are exposed. So I plotted the three NPM micro benchmarks, noisy latency, bandwidth, and bidirectional bandwidth. So we can see that it is getting 1.5 microsecond the MPI point-to-point latency, for other public clouds, this is probably almost 10x higher. But we are getting about 1.5 microseconds. And again, the bandwidth, again, close to peak, 24.6 gigabytes per second, same with bidirectional bandwidth. So it kind of illustrates that there is no overhead from the host layer. So anything that you get at the bare metal, like we can again get here. And this is again same thing for NDV4, but this time our GPU direct, device to device, right? GPU to GPU, again, like two different nodes. So again, MPI latency of D2D of about 2.43 microseconds. Again, the GPU direct RDMA OSC bandwidth, again, close to peak here. And also same here for the bidirectional bandwidth. And finally, yeah, this is a very, very interesting slide, I would say. So these are some scaling efficiency graphs for three different applications. Like, again, Fluent for the different two different models, and OpenFOAM. Really commercial applications, right? So so we scaled it from 2 VMs to all the way to 128 VMs, etc. Again, these are running on Milanix. So like I mentioned, it has the larger cache. And again, the MPI used is HPCX, which is over UCX, right? So, interestingly, like, look at the scaling efficiency, like it goes super linear after some point. Again, the same trend for the three different applications. So the larger cache, it comes into the picture for some time, and after the scaling to some level, and then you get really nice speed up. More details are mentioned about the configuration, the VPN, the software stack, etc., are provided in this particular blog. With that, let me conclude. So it is pretty obvious that supercomputer on cloud is real. Azure HPC Cloud has made into top 500 and top Graph 500 top rankings. Like I was referring earlier, like NDV4 made it into rank 10 in the top 500 earlier this month. And again, rank 17 for Graph 500 using HPV2 last year. The best part is that cloud kind of makes it available for everyone, right? So that's, previously it was, supercomputers were available for maybe national labs or certain universities, etc. But now anyone can access supercomputer, and HPC middleware such as UCX really enable the cutting-edge technology and then get high performance and scalability. With that, let me conclude and have some pointers about getting started, the different VM images that we discussed, how we can quickly deploy the VMs, HPC VM series, GPU VM series, and some performance blocks here. With that, let me conclude, and I can take any questions.
Ethan, thank you very much for presenting some really impressive numbers, like 1.5 microsecond latency in the cloud. That's what you see typically in homegrown supercomputers.
Yeah,
any questions for it? Sorry.
I really wanted to thank the NVIDIA team also for the close collaboration and like making things much better. NVIDIA UCX team, especially like Devender, Josh, everyone really, yeah.
Sure. Any questions from online or for Ethan? If not, I have one question. So
sure.
in terms of UCX, what do you think, what features we are missing, what we should work on in terms of cloud deployments of UCX?
Yeah, I think we have a few, I guess, right? So one of the things, I would say, we had, I think we have a list finally, but one of the things that quickly comes into my mind is Spark, right? So, we had some time back tried to use Spark on UCX and getting into some issues, but that's really something. And then one of the other things is that shared, like intranode communication. There are still some issues, I would say. Like depending on what kind of kernel features are available, etc. So that is one thing. And then, maybe it may not be really a UCX issue, but I would say like we are seeing some kind of some rare issues with DCT as well when we try to scale up. Maybe that's a firmware issue, but yeah, those are the different minor things.
Thank you. Yeah, it seems like we hear shared memory more and more, so it seems like we have some work to do to nail performance there. Any more questions?